Hello and welcome to lesson 1.5, differentials. So up to this point we've been looking at a derivative of y, let's say, with respect to x, for example dy over dx, as a single entity and not a ratio. So what we're going to do is we're going to see that these are two actual items that is actually a ratio, and you can separate the two items. So to understand this idea, let us revisit a derivative we know by analyzing what it means to calculate the derivative geometrically. For instance, y equals x squared. So since y represents the area of a square, let's say, with side length x, so we have this right here. So this, what we want to do is we just want to find the change in area, dy. So dy is found by looking at the change in the side length dx when we see in this expression. So as you can see, this length right here is dx. This length right here is also dx. So the gray areas can be found by the change in y. So dy can be found by x times dx plus another x times dx plus a dx squared. So we can simplify this to just dy equals 2x times dx plus dx squared. Now please realize, as this size gets smaller and smaller, gets closer and closer to 0, it becomes more negligible. But the area now can be divided by just 2x times dx instead. So now you see dy equals 2x dx. And this shows that you can separate the differential. Instead of it being written as dy over dx equals 2x, when y was originally x squared. So you can separate your dy's and your dx's. And this is going to come in helpful, or come in be handy for us in the future. So now we can now list quantities dy and dx as differentials. And this can be used to find approximates of functions. And therefore, if f is differentiable, then you can rewrite your expression instead as dy equals f prime of x dx, instead of dy over dx is the same as f prime of x. So now you can separate items. And therefore, it's just working out, you're still working on a derivative. You're just not working with respect to a specific variable. Okay, so let's show you how you can do this. So let's suppose we have the expression 2y equals x squared minus xy. We want to calculate the differential dy of this expression when x is equal to 2 and dx is equal to negative 0.5. So this is just telling you x is a specific value at a specific point, dx is decreasing at a rate of 0.05 units. So we're going to find this expression. We're using that expression, we're going to find dy. So we're going to just find d of 2y and d of x squared minus xy. And you notice it's just finding the derivative, not with respect to any variable. So the derivative of 2y is just 2. We still got to multiply by dy because it's still chain rule. Derivative of x squared is 2x times dx. Here we've got a product of two functions, so I got to find first derivative of x is just negative 1, multiply it by dx times it by y, and I have to now leave x alone, find the derivative of y, which is just dy. So now I've got this expression. I can solve for dy. I'll notice I'll have two of them in this expression, one on this side and one on this side, but I can substitute other values in first that I have. So x was 2, dx is negative 0.5, don't know at this spot. There's an interesting conundrum. Okay, so how am I going to figure out y? Well, I do have an original expression here. Original expression did have variables for x and y. So I can solve for y in this case. So I'm going to get 2y equals x squared. Well, x squared is just 2 squared minus 2 times y. Okay, so 2y plus 2y is 4y. 2 squared is 4. Y is equal to 1. Now I have a value for y. Okay, so now I'm going to rearrange this. Meanwhile, substituting some values in. So 2 times 2 is 4. 4 times 5 is 20. So that's negative 0.2. Negative, it's going to be plus 0.05 at the moment, times the 1. So that's 4 dy equals negative 0.2 plus 0.05. Okay, so I could add these right now. So 4 dy equals negative 0.15. Now I can divide both sides by 4. So dy. It's just negative 0.15 divided by 4. I'm going to leave it like, it's not like, I don't like that. Let's change it into a decimal. So 0.075, negative 0.075 divided by 2. I'm going to do that again. Negative 0.0375. And there we go. We got our value for dy. Okay. So notice that the only issue with this kind of thing is if dx is equal to 0. If dx was equal to 0, then this differential just won't work. Then the quotient of the differential dy by the differential dx is equal to the derivative. But if dx was equal to 0, then this would just make the entire expression equal to 0. We can also write df in place of dy instead, which is the differential of f, meaning each differentiation rule has a corresponding differential. And you can see the rules still apply. So the differentiation rule that you had before, let's say addition of two functions, or even derivative of sine, still works for differential form. Nothing changes. So knowing your derivatives rules, you know your differential rules. Okay, so let's calculate each differential below and see what happens. So we're going to calculate the differential of cosine 2x. Well, the differential of cosine 2x is just negative sine 2x times 2. Again, don't forget, multiply by dx. Simplify it if you wish. Negative 2 sine 2x dx. Product rule still works as well, so this one, the differential of x is just 1 e to the x, don't forget the dx there, plus, and we leave the x alone, differential of e to the x is just e to the x, times 1 because of the derivative of the exponent, times dx. Simplify this again if you wish. I'm going to simplify it by factoring, so e to the x, 1 plus x dx. And there we go. There's our expression. Now what does differentials mean in terms of what we're actually talking about as their related rate? Okay? So as you can see, based on this function, we have this function f of x as this red function, and we have the tangent at the specific spot x. Now the change in x and the change in y and how it relates to dy over dx is just a slight difference. The dx and the change in x turn out to be identical in size. As you can see, they're right here the same size. The only difference here is the change in y and dy actually turns out to be slightly different. And as your values of x turn out to be the change in x or dx gets closer and closer to 0, you'll notice that that is almost identical. But it does have a slight difference, slight change in the values. So what we're going to do now is we're going to take a look at the difference that we can see if we just apply it to looking at small change in values. So this is what we're going to do. Suppose we want to compare the values of change in y to dy if you have the function f of x equals x cubed plus x squared minus 2x plus 1, and changes from the value of 2 to 2.05. So this one I'm going to use a calculator for, so I'm going to grab my calculator for this one. Some of the values are a little challenging to deal with. But first I need f at 2. So the value f at 2, if I substitute in my calculator, turns out to be 9. I also need f at 2.05 because that's how much the y's values changes. Okay? So now substituting that in to my calculator, I get 0.717625. Oh, my apologies. 9. I already subtracted it. 9.717625. So that means my change in y values is actually 0.717625. Now, let's see how this changed. So now, I'm going to use a differential. So df is equal to 3x squared plus 2x minus 2, which is all going to be multiplied by dx. Now df and dy very similar, but let's see how different it is. So df or dy, if you wish, you're going to substitute the value 2 in for x. Dx in this case, the change in x values is just 0.05. Okay, so I'm going to use my calculator again. Substitute in, this turns out to be 14, this turns out to be 0.05. Half of 14 is 7. This is a little off than a half, so this is going to be 0.7. And then you can see this dy is just slightly off of is 0.7. And that's how they're related. And thus concludes this lesson.